Hi everyone. Before we get started, just check the answers for these calculations. I know we had corrected them in class, but in case I didn't go through any of these for you, just check them before you move on. Now we'll be looking at enthalpy change of specific reactions. So we're going to be looking at delta HF, which is enthalpy change of formation. So it is the specific enthalpy change when 1 mole of a compound is formed from its element in the standard states under this condition. So you need to remember this condition. So 298 Kelvin and 100 kilopascal. So, for example, if we are considering delta HF of methane, methane is CH4. So, enthalpy change of formation of methane will be the energy change, the enthalpy change, when 1 mole of methane is produced from its elements, carbon and hydrogen, in their standard states under these conditions. So carbon is solid and hydrogen is gas. So methane is formed from its elements in their standard states, and under this state hydrogen exists as H2 gas. So this is the equation for enthalpy of formation of methane. So just add an arrow here. So similarly, for C6H5OH, so this is formed C6H5OH. This is formed from carbon, hydrogen, which exists in the gaseous state, and oxygen, which also exists in the gaseous state. So carbon is solid, hydrogen is gas, oxygen is gas, and then we just balance out the equation. So we need 6 carbon and we need 3 H2 and then half O2. So this is enthalpy of formation of C6H5OH solid. Now let's take the example of ethanol. Ethanol is C2H5OH. So similarly, to write the equation, the thermodynamical equation, which represents standard enthalpy change of formation for ethanol, so C2H5OH, this is made up from carbon, hydrogen, and oxygen. As you can see, I'm always starting from the product and then going back to what is forming the product. This is why it's called enthalpy of formation. We are forming this from what elements? So it's formed from carbon, it's formed from hydrogen, and under these conditions, hydrogen exists as H2 gas, so 3 H2 gas, and then half O2 gas. Now moving on, enthalpy change of formation for any element in its standard state will be 0. So normally the enthalpy of formation of an element in its elemental state or naturally occurring state will always be 0, because it takes no energy to form a naturally occurring compound. So you have to be very careful, because it needs to be naturally occurring, which means that you need to check the state of matter at that condition. So these conditions are usually room temperature. So let's check. Sodium, yes, is solid at room temperature. So chlorine is a gas at room temperature. Iodine, yes, is a solid at room temperature, but bromine at room temperature is normally a liquid. So then you will need to supply energy to change bromine from liquid to bromine gas. So in this case, the enthalpy change of formation of bromine gas is not 0, but for the others, these are all elements in their naturally occurring state, so they are 0. for any reaction, if we're starting with the reactants and then we have the products here, we can find the delta HF of the reactants from the elements. And we can find the delta HF of the products from the elements. Because anyway, all the elements found in the reactants will also be found in the products. So, we can have this Hess cycle where delta H of the reaction can be found from the delta HF of reactants and delta HF of products. So if we use the same principle as we did before with Hess cycles, so we start over here from the tail and we go to the head. So like this, which means that delta H for any reaction under standard conditions will be delta H of reactants, negative of this because you can see here we are going in the opposite direction, so negative of this plus delta HF of products. So if we're writing it like this, we can also rewrite it properly to avoid the negative sign at the beginning. So delta H of any reaction is delta HF of products minus delta HF of reactants. But you have to be careful. In these reactions, you will not just have one reactant, you will not just have one product, you can have 1, 2, 3 reactants, you can have 1, 2, 3 products. So in this case, what we're going to do, it's going to be a sum of the enthalpy of formation of products minus a sum of enthalpy of formation of reactants. So we'll include sum in the equation like this. So let's see how we apply this. We have the reaction of calcium carbonate with HCl and the enthalpy of formation of all the substances are given in the table. So calculate the enthalpy change for this reaction. So delta H for this reaction is going to be delta H sum of delta HF of products, so all of these products minus sum of delta HF of reactants, right? And to do this, I'm going to work it out by looking at the products. So CaCl2 over here, so CaCl2, I have the delta HF here, plus delta HF of H2O, which is, so I'm going to put it here, and for carbon dioxide, minus HF of the reactants, CaCO3, plus delta HF of the reactants, HCl, but as you can see here, there's a 2 here, so I'm going to put 2 here. So once I have this equation, I can now plug in the values. So CaCl2, it's here, minus 796. For H2O, it's minus 286. And for carbon dioxide, it's minus 394. This minus for CaCO3, it's minus 1207. And for HCl, it's minus 2 times 167. So you're going to compute this. So you should get plus 65 kilojoules per mole. Let's try one more. So you have this reaction. So these are the reactants and these are the products. So similarly, delta H of the reaction will be enthalpy of formation of products minus enthalpy of formation of reactants. So products, you have CO2. So it's going to be delta HF of CO2 plus delta HF of H2O, but you have 4 H2O over here, so 4 times that of H2O, minus delta HF of reactants, C3H8. And if you look at oxygen, oxygen is in its elemental state. Therefore, enthalpy of formation of oxygen would be 0. So it'd be just plus 0. So you can just ignore the oxygen. So you just plug in the values now. So this is minus 1258 kilojoules per mole. Now you have to be very careful. So this looks okay. It's an exothermic reaction, burning. But you have to be very careful. It's asking you enthalpy change, not for this reaction, but for 11 grams of propane. And when we calculated, this is for 1 mole of propane. So we need to find the number of moles of propane in 11 grams. So number of moles of propane. Propane is C3H8. So number of moles will be mass divided by MR. So 44. So based on the delta H, we understand that each mole produces minus 1258 kilojoules of energy, which means that 0.25 mole, which is equivalent to 11 grams, this would be, so minus 1258 times 0.25. So this would be minus 314.5 kilojoules. So this is what's going to be the answer. So you have to be very careful for these questions.